Hey! In this video, we're going to be using QC to predict the direction of a reaction. So this is kind of a follow-up to our KC questions that we've been doing before, and it's kind of an easier step than when we were doing questions where we had to solve all of the different concentrations at equilibrium. So we still start off with a balanced chemical equation. So a 2NO plus an O2 gas, and it's a reversible reaction with 2NO2 gaseous. And just like Kc, we can create a QC equilibrium expression. A QC equilibrium expression, and it's still the concentration of the products. And it's a coefficient of 2, so it's squared. And it's all over the concentration of the reactants, and it has a 2, so it's also squared, and our oxygen. And we've been told that at some temperature, whatever it happens to be, that for this reaction, Kc is going to equal 60. This is the information you've been given. This is usually the setup to solving concentration. And you've been told that initially, yes, you've been given that initial flask. You have a concentration of NO equal to 1.5 molar, and you have a concentration of O2 equal to 2 molar, and you have a concentration of NO2 equal to 2.5 molar, and this is usually the time where I tell you, you put this into a flask, put a stopper on it, put your snowshoes on, go for a walk out in the woods, have some fun, come back, and now calculate the reaction concentrations now that it's at equilibrium. With QC, you don't actually have to calculate the final concentrations. QC predicts if it's going to move to the right or to the left. So in our QC equation, we're still going to fill in these concentrations. So NO2 is 2.5, and we're going to square that, and that's all over a 1.5 multiplied by a 2, and we get a QC value equal to 2.08. But what do we do with it? What do we do with that? So I'm just going to slide this up, and we're going to take a look at something here. So we have that QC was 2.08, and I want you to remember that for this reaction, the Kc was 60. When we calculate QC, if QC is less than Kc, the reaction will move to the right. Move to the right, making more products. Oh, that's what'll happen. The alternative is that if QC is greater than Kc, the reaction, yeah, you got this figured out, you know where this is gonna go, the reaction will move to the left, making more reactants. Now there is a possibility, okay, there is a possibility, hear me out, that QC could be exactly equal to Kc. So I could make up a question and you solve QC and somehow you got a QC exactly equal to 60 and you'd be like, what do I do now? If somehow your QC is exactly equal to Kc, QC equal to Kc, already equilibrium. Somehow you put in your flask the exact concentration of all chemicals required for equilibrium. In this case, 2.08 is less than 60. That means it's the first case here of QC less than Kc. This reaction moves right. So it's going to move to the right. We don't actually have to calculate all of the concentrations here, but we do know that it's going to move to the right, and that's all QC does. QC predicts which way a reaction will go. I'm going to do one more example here. Let's go ahead and scroll this up and get it out of our way, and we're going to put a brand new equation down here. So this time it's going to be 4 NH3s plus 5 O2s, and if you did my other KC videos, I've used this equation before. I like this one because it has lots of big, beefy coefficients. And 6 H2O, a gas. And you've been told that at some temperature, it doesn't matter, it's some temperature for this reaction, our Kc is going to equal 850. We're going to calculate QC, predict the direction of this reaction. We set up our equilibrium expression. QC is equal to the concentration of our products, the first one being NO to the power of 4, the second one being water to the power of 6. It's all divided by the concentration of our reactants. Our ammonia to the power of 4, our oxygen to the power of 5. Yeah, it's going to be some wonky numbers, but we got calculators. We can do this. You would have to be told what the initial concentrations are. So you would be told that initially, in a flask, we're going to place a concentration of ammonia equal to 0.5 molar and a concentration of oxygen equal to 0.75 molar, a concentration of NO equal to 2 molar, and a concentration of H2O equal to 1.5 molar. And that's what was put in our flask. So that's what we're starting off with. We take that flask, we put these in, we put on a cap, we shake it out, we go play with the cat for a while with a ball of yarn. But when we come back, this time we don't have to calculate all of our concentrations. We just have to predict, did we make more reactants or did we make more products? This reaction is going to go one way or the other, towards the reactants or towards the products. Let's go ahead, fill this into QC. In our QC expression, we just fill in each of our concentrations into the equation. So we get 2 to the power of 4, and our water was a 1.5, so that goes to the power of 6, and our ammonia, that was a 0.5 to the power of 4, and our oxygen, 0.75, and that's to the power of 5. And then we need to give ourselves a little bit more space here to finish this off. We are almost done. We're going to chug this out into the calculator, and we get QC equals, I'm just going to do this in 2 steps, 182.25 all over. We put in all those values in the bottom. We get 0.01483 for a QC value equal to 12,288. And we're comparing that to a KC of 850. Because QC in this case is greater than KC, this is a situation where the reaction moves left. We make reactants. And that's it, folks. That's how you use QC. So it's a little bit easier than solving concentrations. I hope you found this video very, very helpful, and I'll be looking forward to seeing you next time. Thank you very much.